Okay, welcome everybody. And a quick introduction, an overview of what we have. And the website is this github.com, and then it's CompPhysics here, and then CompSci program. And this is where you will find all the material which is relevant for the course. So the first thing is actually this very, very tentative sketch of possible projects. So what we're going to do now is to actually go through things which some of you may find simple or which you may have seen before. We are going to use this kind of machine learning path to remind ourselves about many of the standard computational science algorithms like matrix inversion, singular value decomposition, optimization techniques, and so on and so on. And we are going to link them with explicitly with machine learning topics. So we are going to take a path which where we want to actually catch many birds with a stone and also adjust the way we proceed according to your background. And as you know, I mean, and as we saw last time, you are a pretty heterogeneous group, which means that people come with different backgrounds. Some people are very savvy when it comes to computational methods, others are not. So I hope you're able to find some kind of middle way here. If not, you should let me know, and we can try to tailor things more to your own needs. So, but the idea here is to use methods from numerical science in applications towards machine learning and artificial intelligence. So that way we hopefully were able to combine both and also tailor the projects to your own needs and scientific interests. What you will find is a link down here. So after every lecture, I'm going to actually upload the video and also handwritten notes. So you can always watch the handwritten notes and the videos. And this is a very tentative schedule on how we're going to proceed. It may happen that if somebody is away, you can always rewatch the video. And it may happen that in November 30, I may be in Spain. So then I will just upload a video. And here you see roughly the schedule. And it takes into account the winter break, obviously, from December 14th. If you're away, you can always watch the recording. And you can attend via Zoom if that fits better. So there's no problem. I mean, you don't need to be physically here. So this is very much up to you guys. So the links which are perhaps more interesting ones are the one which links to lecture notes on machine learning. So these are kind of textbook I've been developing over the last 2 to 3 years. But then we have the weekly material. And this is the one which I wanted to discuss with you today. And you will find typically the material for the different weeks. So this is just a kind of rough plan for what we are going to do before the winter break. So I wanted to give you a kind of introduction first with linear regression and topics like that, because that's going to set the scene for some of the first, let's say, numerical methods like matrix inversion, singular value decomposition, which is, so how many have heard about the singular value decomposition theorem? Only 2, 3 people. That is the most beautiful algorithm you can think of. So any matrix, even a singular matrix, can be decomposed in terms of what's called the singular value decomposition. So in terms of 2 orthogonal matrices and 1 matrix which is diagonal, which contains the so-called singular values. So any matrix can be decomposed. And that's going to allow us to make some mathematical interpretations of the machine learning methods. So the kind of philosophy here is that many of you have actually seen machine learning methods, but probably you've handled them as black boxes, right? So how many of you have gone behind the mathematics of machine learning algorithms? A little bit, yeah. So which means that we can actually try to combine computational physics or computational mathematics or numerical mathematics with machine learning, and then look at both the mathematics which is behind the methods, discuss the algorithms so that we get a more, how to say, we move beyond this kind of black box attitude towards machine learning. And the whole idea is to demystify it in terms of computational techniques and the mathematics. So there are fields in machine learning, like deep learning, which doesn't have a sound, or you see, what you might call a rigorous mathematical proof of what happens and the way you build up a deep learning model. There's something like the universal approximation theorem, which states that a neural network with at least one hidden layer can approximate to a given error a continuous function, but it doesn't say anything about the architecture of a neural network. So this is an emerging field, actually, the mathematics of deep learning. And it means that in some of these applications, we will not have a kind of rigorous mathematics for why things work. And then we have other methods which are essentially applications of linear algebra. So if you think of linear regression, there is a linear algebra path which we can take there. And that's going to involve a lot of techniques like matrix inversion, gradient calculations and gradient optimization. And then we have other methods like support vector machines, which is essentially, support vector machine is essentially a convex optimization problem, period. And which again leads to solving linear algebra equations. So linear algebra is going to pop up again and again. And hopefully that will give you a better feeling of what these methods are in conjunction with the machine learning methods. So what I wanted to give you today is a kind of, first a quick overview and motivation. And then we are going to look at the gritty nitty details of the standard linear regression techniques. And we may also dive into, if there is an interest, into something which is called Bayesian linear regression, and perhaps also kernel regression, which are the more advanced methods. And some of you may have heard about these different techniques, right? Any questions so far? Things which are unclear? So I'm going to abuse a little bit in the beginning with slides. I like to break the monotony with a whiteboard and slides. But in the beginning, I just need to go to have you digest some slides here. And these slides contain textbooks which you can look up. And some of these textbooks, like the textbook by Hastie, Tibshirani, and Friedman, that is a kind of classic nowadays. For those of you familiar with statistics, it's actually an excellent textbook, and you probably met the textbook. If you're on a UIO IP address, you can download it for free from the Springer server. Are you familiar with these kind of things? So you can download the Springer text. So it's a Springer text, and you can download it for free here. And the textbook by Goodfellow, which is actually called Benjo and Coville, called Deep Learning, is a kind of standard text when it comes to deep learning methods. And it has also lots of links. So some of these texts, be aware of the fact that they sometimes they can be a little bit sloppy with the mathematics, or they can just state things. That's often a drawback with many of these textbooks in machine learning. Some may be heavy on applications and be very sloppy on mathematics. Some of them may be a mix. So like the textbook by Bishop is a pretty good one. It has more emphasis on the statistical part of machine learning. And then if you wish to, you can also look up the lecture notes which I provide you with. So they can be seen more as a kind of an overarching view on what is interesting to look at and what kind of material you could dive into in order to get a deeper insight. Yeah, this is just a reminder. And then after the lecture, I normally put up the video of the lecture, so you will get that one. But this is just the Zoom link. If you're interested in using Slack, I mean, Slack is not supported by the university here because it breaks the GDPR laws in Europe. But the university uses Facebook, which is much, much worse than Slack. So it's a totally inconsistent thing, actually. So we are thinking of having 3 projects. And if you already have found somebody you want to team up with, feel free to do that. typical working groups, 2 to 3 people, but last year we had 5 people joining. So this is up to you. And actually, this is something which was pretty successful last year. And we could, if you have data which you find more interesting than the vanilla data which I proposed, let's say for the first project, you could present this data to everybody else here. And maybe everybody wants to look at that specific data set. So this is very much up to you guys. So I'm going to just propose a framework, and then you can look at it and say, no, I didn't like that. I want to do something else, right? So we should have this kind of flexibility, right? And we could also do that with the other projects, to actually organize them as a kind of workshop where we discuss a specific data set, and then maybe that triggers everybody to look at the same data set. So I was thinking of some kind of, these are the just the coordinates. So Anders Kvellestad is actually the expert on Gaussian processes, and he's gonna join us a little bit later. That means in the spring next year. So I typically go through most of the material which is relevant from project 1 and 2, and then Anders takes over during the second half of the spring semester. And he has his office actually nearby here, just over in that corner. So these are very tentative. These are for your planning. And I don't want to have something before the winter break, because I guess people, you need some time to get to adjust to your new projects and get up to speed. Actually, we can have a very, very lax attitude to the deadlines. So the deadlines are for your planning. Last year, what happened was that some people actually merged together project 2 and 3. And because they had a data set, they wanted to study with different methods. So they used Gaussian processes and Bayesian statistics, and at the same time, standard machine learning techniques. So that's also fully possible. You can merge everything into, let's say, project 2 and 3 into one big project. Alternatively, you could do that with project 1, 2, and 3, if you have a kind of thread which goes through all of them. So this is very much up to you. We want this to be as research-based as it can be. At the same time, if you feel not comfortable with that, we can always you can just follow the recipes which we outlined for the projects. So there's no, how to say, maximum flexibility. So you will find the lecture notes, and we have these different textbooks here. There's also a textbook by Aurélien Geron, who was one of the people behind TensorFlow in Google. And this has a lot of hands-on codes, and a pretty useful one. I actually stolen many codes from the textbook of Geron. Also, we discussed, for some of you who were not too familiar with Git and GitHub or GitLab, we discussed that a little bit in the morning. We expect that you're actually familiar with that. When it comes to Python environments, Jupyter notebooks are pretty standard. And Jupyter stands for Julia, Python, and R. You can run R code in Jupyter notebooks if you prefer that. If that's something which is closer to what you've seen before. But the community is now moving more and more into Python mode. So that's taking over. And I guess the number of Python users and R users when it comes to machine learning, that they were close to the same from a few years ago, but the average age of the people using Python was much, much lower. And if you're interested, if you would like to know more about specific things, because we are going to go along a specific path. So we have, and especially there's one course which is run by people in statistics, which actually follows this course pretty well, but it's a course in the fall semester, so it will be too late now. But if you're interested in the statistics, to go deeper into a statistics direction, the course which Ricardo de Bin is running is actually pretty good. And this is this one here. But that's a fall semester course. Then there are many other courses actually. So we have this one, which is called Machine Learning for Image Analysis, which can be quite interesting for many of you if you go into the imaging direction. So this is really tailored to imaging. So that is a spring semester course, and that's been a course which many have taken. I mean, you have 30 credits you need to take, so, but you're not limited by 30, right? So you can take more if you want to. And being registered as a student here, you can just follow courses as you want. And then, depending on your interests, there's actually one on applied Bayesian statistics. Unfortunately, this is a fall semester course, so it would be too late. The same with the deep learning here, whereas this one is a spring semester one. So these are just, you have access to all these links here. Yeah, I'm not going to read everything here, so by obvious reasons. But what I wanted to say is that when you think of machine learning, there are many ways of looking at it. So the traditional way, which you will find in many textbooks, which don't include the subtitle as statistical analysis, is something which is based on a frequentist approach. I don't know if you're familiar with, in statistics, you have two kind of main approaches. It's a frequentist approach and a Bayesian approach. Now, the frequentist is it's a different philosophy in the way you define the probability distribution behind the events you have. In the frequentist approach, which has been the kind of, so this is a kind of exaggeration because these two approaches actually, there's a kind of floating transition here. But traditionally, when you look at the frequentist approach, what people have been interested in is to be able to make predictions. So that means you fit a model to your data and you use that model to make a prediction. So suppose you want to fit a continuous function and you fit that with a polynomial. That is your model. And then with that fit, you can make predictions with the model you have developed on data which was not included in the training. So linear regression is a typical example of that. So if you can actually fit everything with linear regression, just linear algebra actually, then there is no need to invoke any kind of advanced method. So the standard frequentist approach, you can derive a probability distribution, but there's been less focus on that. So you're interested in predictions and then in correlations among the data set. So just to give you an example, there is a famous cancer data set from Wisconsin where they looked at breast cancer, and that data set has something like 30 features. And the features are like the radius of the tumor, the thickness, color, and things like that. And then clearly, if you look at something like the perimeter of the tumor, you would think that to be correlated with the radius, right? I mean, the perimeter is just, we know it's proportional to the radius. And you would find then that when you look at something which is called a correlation matrix, there will be strong correlations between these two quantities. Then there are other quantities which have less correlations. So standard machine learning based on a frequentist approach has put less emphasis on the probability distribution behind the input data and the output data, and more on predictions and correlations. But this is, as I said, is a kind of, to me, it's a kind of awkward distinction. And then you had the Bayesian approach, where you're more interested in finding a probability distribution based on an ansatz for the original distribution. Then you can find and train a model which gives you a probability distribution. And with that, you can estimate the errors of, let's say, the mean value, the parameters of your model, and so on. So error estimation is also a very important thing. And with a probability distribution, you can look at causations. What is the likelihood of finding B given A? Now, we as scientists, we are interested in all these things. And then depending a little bit on which direction you go, you could have a direction where you're more interested in just making predictions and finding correlations in data. But keep in mind that you can always find a probability distribution also from a frequentist approach. In the statistics environment, there used to be two kind of different camps, and they would fight each other quite seriously. And there's a textbook here by Ian Murphy, which is called The Statistics of Machine Learning, where he actually uses a whole chapter on just denigrating the frequentist approach. So, but this is not, I don't find that very interesting. So just keep in mind that when we look at many of the standard machine learning texts, it has often been there's been a smaller focus on a statistical interpretation. So I'm going to bring in these elements gradually. But if you really want this kind of statistical interpretation, this course STKIN-IN 4300 contains many of these discussions by actually a statistician who's a frequentist by training. So when you look at the types of machine learning which we are going to deal with here, we are mainly going to deal with supervised and unsupervised learning. So supervised means that the data has been labeled. The unsupervised means that you don't have labeled data. And you know that labeling the data is expensive. And in many, many experiments nowadays in science, you produce terabytes of data. So if you look at an experiment at CERN, that's my reference frame, I'm in subatomic physics. If you look at an experiment at CERN at the LHC, you produce something like petabytes per second. And these are compressed down to gigabytes. And if you run your experiment for half a year, which is a typical experiment at CERN, you can do the math and find out how many bytes you're storing and the amount of data. And there is no way a human can traverse that data set. There's no way. So in my own field, nuclear physics, we've been using unsupervised methods on recognition of specific events from collisions between particles. And there we've had data sets of terabytes. And the last time a human actually went through that data set, it took that person something close to a year. And that's just a waste when you can do unsupervised learning and do a pre-classification in a few seconds or just a few minutes. And then you can use your insight to figure out whether this unsupervised learning method gave you the right clusters of data. So these are basically the two types of things we are going to look at. And then we are going to mainly look at classification. So think of that as discrete outputs, true, false, yes, no, different classes. So these are the discrete outputs. And then we're going to look at regression, which normally means you want to fit a model which reproduces a continuous function. So there is an assumption that there is a continuous function which represents your data. And then when you've done that, you can then run your favorite method. We have clustering, which is another type of common task where you try to cluster events in blocks, and this is normally used in terms of unsupervised learning. But these are the kind of most common tasks which we end up dealing with. And we are going to start with regression and linear regression. So you may ask, why is linear regression, which you can derive from standard linear algebra, why is that included in machine learning? Any good ideas? Are you familiar with it, linear regression, what it means? Ordinary least squares, does that ring a bell? Okay, that's plain linear algebra, right? You just inverting a matrix. So I don't know how familiar you are with machine learning, but if somebody has made any kind of thoughts and thinking about what linear regression, why that could be included in machine learning? Any ideas? I'm not expecting that you have an answer here. Yeah? Yeah, I was thinking more, why would you include linear regression in the family of machine learning methods? Because if you think of machine learning, you would think of that as something where you let the machine actually learn about the data and find the best possible way to represent the data, right? That's a kind of definition of machine learning. Let's see if we have some.
The structure is quite the same.
Yes, sir, yeah.
The structure is quite the same.
Yeah.
The matrix, the weights that the machine learning has to find is a matrix, and then you have
exactly.
Plus one bias.
Yeah, that's a very good answer. So the structure is the same, and you can actually do a statistical interpretation of it. So we are going to use linear regression, which I normally call low-level machine learning. Some people may get offended because kernel regression is actually quite nice, but it allows us to catch many, many birds with just one stone. Because as Chiara says, I mean, it has the basic way of thinking, which we include in machine learning. You have unknown parameters which you want to optimize. So you have the optimization problem. We can actually give it a statistical interpretation. We can derive the same equations from a statistical interpretation. It contains also many of the elements which are very useful to build up a basic understanding of some of these central topics in machine learning, like overfitting and underfitting. And that leads to something which is called the bias variance trade-off. It has analytical expressions for the parameters, the unknown parameters. Analytical means that you have to invert a matrix. It has analytical expressions for the expectation values. And it has analytical values for the variance of the estimators, or the what I would call the parameters of the model. So that's is something which is extremely useful from a pedagogical point of view. And if you can fit a function with standard linear regression, there is no need in going to more advanced methods. It's included in, even if it's a very deterministic model, you just have to invert a matrix. It contains many of the basic elements. And hopefully, when we now move through the rest of the semester till the winter break, that we have been able to build up this kind of intuition and understanding of what enters a machine learning algorithm. So I'm going to repeat many of these things, actually. So I wanted actually to give you two of the basic elements. The first is a data set. So that's your input and output data. And then there's a huge debate, what is the model? So this is something which we are not going to answer. You can actually use Bayesian statistics to do a model optimization. So that's a very interesting field. But we are just going to assume that we can have a specific model, and then we're going to try to reproduce the data. But you could have a totally crappy model, which gives a perfect reproduction of the data. So this is as a deeper philosophical issue. What is the correct model? And we are going to be a little bit lax with that. But the model is a very important thing. And when you have a model, we are going to need to assess whether this model is a good one or not. And that leads to a function which we have to define, or which we have to choose. And this is normally called the cost function or the loss function. You may find it named, if you go to finance, people will call it the risk function, or some people even just call it the error function. And when you have this, what you need to do then is to optimize this function, which depends on the parameters you've chosen. And then when you optimize this function, that is when you find the optimal parameters of your model, for your model, which describes the data in the best possible way. So let's break this down a little bit and just look at the whiteboard. So the last ingredient, so these are the three basic ingredients. And when you're done with that, at the heart of every machine learning algorithm, which we are going to go through, there is an optimization problem. So the nice thing with linear regression or ordinary least squares and variance thereof is that you have analytical expressions for the unknown parameters. And that allows us to build up some basic intuition about what's going on. One of the big problem is actually to calculate the derivatives, because you're going to deal with a multi-dimensional space of parameters. You don't know when you do a neural network whether your function is a convex one, whether it's a concave one, whether there exists a local minimum or global minimum. You won't have any idea about that. For linear regression and these methods, we actually have a function which you will see a little bit later is a convex function. So there will always be a global minimum for the linear regression methods. However, when you move to more complicated methods, then evaluating the gradients. So if you have a neural network, it's not uncommon that you have millions of parameters to optimize. So that means you need to calculate millions of gradients. And the big bottleneck in basically all the machine learning methods lies in the optimization part. So if you want to have many new friends, I'm not inferring that you don't have friends, please. But if you want to have many friends who will cite you, then you can actually dive into this field of optimization. There is a method which is called ADAM, is an adaptive momentum method. And I don't know if you looked at the number of citations of that paper. It's published in a journal for machine learning. It has more than 120,000 citations, and it came in 2014. That sets the level. A good paper, a good scientific paper has 100 citations or more. That's an excellent paper. That sets the standard. So these kind of problems are really the bottlenecks. And we are going to see different ways by which we're going to tweak these gradients and actually do the gradient, what's called a gradient descent method. Okay, so I'm just going to bring up some definitions before we take a small break here. Many of these things are things you can actually look at, and there are also things you need to install, Python installers, etc., etc. I'm not going to go through that. I hope you can, because I know that most of you have done some programming. So, but you will get some practice when you look at some of the first exercises. So here in the beginning, you will find some practicalities, installing R and C++, Python. There are numerical packages and important libraries for linear algebra. And one of these is called LAPACK, which is linear algebra package. And that links with something which is called BLAS, which stands for basic linear algebra subprograms, which essentially deals with efficient matrix, vector, and vector or matrix scalar multiplications. So these are libraries which you probably have encountered, and you will find some basic properties here, but I'm going to skip that because I'm in a way, this is just more like a review. If you haven't, most likely you've seen these things before, and you can just review and go through it, and you will see some simple Python codes. By the way, if you look at the text, the material here, you will find the material in terms of plain slides or as a Jupyter notebook. So that means that you can take everything and just the weekly material and just run it as a Jupyter notebook. Okay, I'm going to switch a little bit to some of the basics here, and we are going to look at linear regression, some of the basic elements here. Can you all see well? So these kind of handwritten notes is something which I also will put online after the lectures. So if we now look at linear regression, which is going to be our first linear or machine learning method. And let's repeat the basic steps here. So what we have is our data, and I'm going to label this as input data and output data. So we could think now of a domain of data where we now have sets of So I'm starting with 0 as my first element because Python arrays and C++ arrays start with element 0. So you could start with 1 if you don't like that. And then I have an x0, so that's going to be my input. And then I have a y0, that's my output. These quantities have different names, but I'm going to essentially to call them inputs and outputs. And you will find them named as targets or whatever. There are lots of different namings depending on the field you're dealing with. And we have a set of these data sets up to some n minus 1 and y of n minus 1. Now, I may not specify whether these are vectors or scalars. So the x's could be vectors which contain information about different features. So suppose you have like a data set, this cancer data set which I mentioned. The output would just be true false, whether this is a benign tumor or a malignant tumor. But the x's could now contain one row, it could be a matrix or just a vector or column of that specific input data matrix, where you would have a given number of patients, which is the n you see here. So this could be a given number of patients which have been surveyed. But then the x could contain different features. So like the first x0 could be the radius of the tumor. The next one could be the specific area of the tumor and so on. And we are coming back to this. I'm going to give you examples of what it means. So when you look at my notations, it should be clear from the context whether this is a vector, a matrix, or a scalar, or a tensor. So I'm just leaving, I'm not going to put bold symbols or arrows or things like that, okay? So let's assume now we have the data set. So this is the first element, and that was the element 1, which we named here. And then we need a model. So that would be the next piece. And in our case, there is actually, for linear regression, there is an overarching model, a basic assumption about your data. And then you're going to develop a model to reproduce that data. Then we have the so-called cost or loss function, risk function, etc. And this is the way we use to estimate the quality of the model. So the way we estimate or gauge, we estimate the quality of the model. So I'm going to put this quality in quotation marks because I haven't specified what I mean with that. So these are the basic 3 ingredients. Now, there are some assumptions in linear regressions which we are going to, which we need to define. So in a certain sense, you could say now that this is a kind of model itself. So we are assuming now that this y, this output which we have, and now you can think of this as a vector for the y zeros and so on. This has a dependency on x, which is given by a function f of x. And we assume that there exists a continuous function. And one of the assumptions is actually that this is a deterministic continuous function. And then we have some noise, some epsilon, and this is given by, so this epsilon is proportional with, when I use this n, this is a normal distribution, and with 0 mean value and a variance sigma squared. So we have a noise which is normally distributed with a mean value and a given variance. We don't know that variance, and what you will see then often is that people just put it to 1. So this is you can read this as a noise to the data. So in a certain sense, you might think that this is already a kind of model about your data. Now, the deterministic thing means that the x's are not seen as stochastic variables. The epsilons are seen as stochastic variables. In many machine learning applications, we may not be interested in the probability distribution of the y's. We're just interested in fitting a model. So you can argue why you could think of f of x as a deterministic function. Because suppose now you're making a survey over, let's say, voting preferences. The questions are already set. So there's nothing stochastic with the questions, right? So they are set. And the response from people, there's nothing stochastic with that. I mean, if I were to pick all of you, this is a choice I made, and that would be a pretty deterministic choice, right? And then I would have a preset set of functions, and then that would be my function f of x. And then I could ask, what is the output for you, selecting a specific political party? Or you're running an experiment where you fix the beam of particles. So that's the incoming beam, which impinges on a target, and that produces an output after a collision with the particles in the beam. So the beam is then well-defined. It has a specific frequency and a specific energy. And you're assuming now that this energy is so well-defined that there is nothing stochastic about it. So that could be an example of why we could now say that f of x, that there exists a deterministic function. We don't know the function, okay? So what we are saying now is that we, in a way, you could think of this as a kind of overarching model assumption about your data. But then we make the model, and this model which we're going to make now, this is an approximation to f of x. So we're going to assume that f of x is now being approximated with a y tilde of x. And then we have to train a model. So if we now look at this specific model, we are going to introduce some quantities now. But let's take it the simplest possible way we can define a continuous function in terms of a model. So the simplest one is just have a polynomial approximation, right? So if I look at the specific data point now, suppose I have this x of I, which I'm going to label y of I. I can now approximate that one. So if I now take away the noise which I have, so I'm just going to take away the noise, I'm going to approximate that one with a y tilde of x of I, and this is equal to y I of tilde. And this y I of tilde could now be a polynomial. So assume a model now, a polynomial model. Polynomial model here. So that means that we have a y of I tilde is now going to be given by a sum from j equals 0 up to some polynomial degree. And then I have some unknown parameters, beta of j. And then I have my x of I to the power of j. And you see that this one has the intercept first, plus the slope, which comes in here. And then I have x of I to the power of 1, plus beta 2 of x of I to the power of 2, etc., etc. So this is my polynomial fit. And P is normally less or equal than the total number of data. So I'm going to call every polynomial degree as a feature or property. This is pretty common in the literature. And I'm going to rewrite what you see here as a matrix inversion problem to find the parameters beta. And that's the standard ordinary least squares. So you guys have been extremely patient, and there is a reward for that. It's a small break, actually, 15 minutes. And I'm gonna try to stay within these 45 minutes. and not try to exceed, because my attention span is something like 10 minutes. After that, I start daydreaming and I don't listen anymore, right? And I guess you're not that different from me. Maybe you're more careful than me. Okay, let's just put the recording on pause. Okay, so what I want to do now is actually to go through many of the basic ingredients in machine learning by using this polynomial approximation, because that's something which is easy to relate to. Now, if you now look at what we have, if you now write out the equations, you can easily see that you can translate everything in terms of a matrix times a vector problem. So if you look at this data set which we have, so this will be our y over I tilde. And now we are going to rewrite this in terms of a matrix times a vector. And you can see that immediately if you now write y0, this is going y tilde 0. This is going to be given by beta 0. And then I have a beta 1 x0 plus beta 2 of x0 to the power of 2. And this goes all the way up to beta of p minus 1 of x0 to the power of p minus 1. And unsurprisingly, beta y1 is obviously beta 0 plus beta 1 x1 plus beta 2 x1 squared plus, and then beta p minus 1 of x1 to p minus 1. And then we can go down to the last data point, and we are assuming now that p is not the same as n. You could put p equal to n, and then you're going to get a matrix which is pretty famous in linear algebra. It's called a van der Monde matrix. But now we are simply making the assumption that we are not the same number of data as we have the polynomial degree. And this will be a beta 0 plus a beta 1. This is not very exciting. Beta 2 of xn minus 1 squared, and then all the way to beta of p minus 1 of x of n minus 1 of p minus 1. And when you look at this now, you see that you can rewrite it in a more compact form. If we now define a vector y tilde transposed, which is actually equal to y0 tilde as components y1 up to y of n minus 1. So this y tilde is now a vector with length n. I can define a new vector beta, and this vector beta transposed is given by beta 0, beta 1. These are the different components of beta p minus 1. And then we see that this beta has length p. And when you look at the structure here, you see that you can rephrase this as a matrix times a vector. So we can actually rewrite this vector y tilde in terms of a matrix X multiplied with a vector beta. And this matrix X, in our case, is simply going to be equal to 1s here. So this is in the polynomial fit, so these are dots, down to 1. And then we have x0 to the power of 1 of 2, and all the way of x0 to the power of p minus 1. And here we have xn minus 1, xn minus 1 to the power of 2, and xn minus 1 to the power of p minus 1. Or in a more general form, we can now write this out as x00, x01, and all the way up to x0p minus 1. And then I have x10 down to xn minus 10, and then xn minus 1 of p minus 1. I hope that doesn't come as a surprise. So the last one is a more general term. This matrix has many names. So this is often called a design matrix because the way we have designed the model, or feature matrix, or property matrix, and so on. So there are different names. So I'm going to use often design matrix or feature matrix. So you could now think of every column which you see here representing a specific feature or property of the polynomial. Now, when you go to the cancer data, you could now think of the rows as the number of patients you have, and each column could represent a specific feature of the tumor. So it could be the thickness of the tumor, it could be the radius of the tumor, it could be the color of the tumor, and so on and so on. So this quantity here has many different names, but I will essentially use the design of feature matrix. Now, one thing which we're going to meet a little bit later, which is important for us when we are so-called normalizing the data or scaling the data, is that many of the algorithms, they don't include the intercept, especially, and this is relevant when you're dealing with a polynomial. So we are coming back to that because that's something which causes confusion. So it's common to scale the data so that every column here is scaled by subtraction of the mean value of a column. We are coming back to that. And this is done in a way to avoid outliers in your data, which then can penalize the fitting of the model by giving you a large error. So if you now look at what I did here, if you look at this equation, so X contains now the complexity of the model, and it's solely defined by the input data. So X is now, if we assume that the data are given by deterministic variables, so there's no stochastic, no randomness in the X's, then X is a deterministic matrix, period. The other thing is you see now the model is linear in the parameters beta. And that's why it's called linear regression, because it's linear in the unknown parameters beta. So let's just mark that. And since I have many colors, I can actually use colors here. So linear in the unknown beta. So beta are the unknown parameters. Beta. So we've set up a model, and then what we need to do now is to decide whether this is a good model or bad model. And if you now think of ways to assess whether this is a good model or bad model, there are many mathematical functions you could use. So let's look at that. So how do we assess? So this is a final part. Now we have a model, we have the data, part one, we have the model, part two, and then we need to assess how to assess if this is a good model. So let me try to trigger your intuition now. If you want to, if somebody gives a model and then you have the data, you then ask yourself, what kind of measure can I put up in order to tell, let's say, Oscar here, that my model is the best one possible, right? So which kind of mathematical model could you think of? Now we are looking at continuous variables, right? So kind of functions. So this actually leads us to what we call the cost function or the loss function. So normally the cost function is the total function, but many people call this, so this is a function of the parameters beta, the unknown parameters. And we want to minimize that one. So what kind of way, which kind of ways could we actually set up a mathematical function to assess the quality of the model? What comes to your mind? The error. Absolute error? Yeah. So the absolute error is a very good choice. So what we would do then is actually to write C of beta equal to y of, and now I'm writing this as a vector. So when I don't put the subscripts, these, in this context, these are vectors. And then I would have y minus y tilde, which in our case now is simply equal to the data which we have, y minus this x times beta. And I'm going to rewrite this in terms of, since this is now the absolute value, I'm going to write this in terms of the norm 1. Are you familiar with that notation? So let me just quickly, so the norm 1 of a vector is actually the sum over all the components of the vector n minus 1 of xi. That's the norm 1. So these are just more compact notations which I'm introducing here. And you've probably seen them before. That's one way. That's excellent. Other ways of, let's say, clearly if the norm 1 is 0, then we have a perfect model, right? Other functions which we could look at? Yeah, there's a famous one, or just a mean squared error, right? So we could now take another function which is given by c beta, and now I'm going to rewrite this in terms of a statistical expectation value, but it's the expectation value of the sample of events. So I don't have the probability distribution. So I'm going to take over all the data set, and this runs from I 0 up to n minus 1. So I have my y of I minus my y of I tilde squared. This has a name in the literature as the mean squared error. Okay? And then I can rewrite this one now as 1 over n. I have a sum of I equals 0, n minus 1. And now I'm plugging in the model which I have. So this goes from j of t minus 1. And then I have my xi times beta of j squared. This is nothing but a specific row in my design matrix multiplied with a column vector beta. So this quantity you see here. So if I take a specific, if I take a specific row here, let's say this row which you see here, what I have now is just beta 0 multiplied with the different elements of that specific row. And I just opted, instead of having this specific here, I opted for the general labeling here. Is the linear algebra okay? So sometimes sometimes since you practice linear algebra, it takes some time to get up to speed again. I hope it's not too slow and that the pace is okay. And just let me know, just shoot me an email if whether these things are too simple or whatever. I'm trying to find the right level because I mean, you have people from different, as we said, I mean, your background is pretty varied. Now we can rewrite this one in terms of a norm 2. So we could rewrite this as a norm 2, and then I just write this as a y minus x times beta. This is norm 2, but it's norm 2 squared, because the norm 2 is actually the square root of the sum of all the squared values. So just remind you of a norm 2 of vector, that is actually given by the square root, and then I have an I, 0, n minus 1, and then I have xi squared. So these are just definitions now. But now it's useful to actually take a look at what we are going to do now. So if I want to find the optimal parameters beta, what kind of mathematical procedure or mathematical method would I use to find the best parameters beta? There is a mathematical operation which we can use to find the best parameters beta. What comes to your mind as a the way you would now we want to find the optimal beta, which minimize either the mean squared error or the absolute value. So what would you do? What kind of mathematical operation would you invoke in order to be able to do that? Yeah? Yeah? Yeah. Take the derivative, right? So what we're going to do then is actually we are going to look at the derivatives of this quantity beta of d beta j. That's what we want. But now comes an interesting thing. So the two functions we have are two very viable candidates for estimating the quality of the model. So all of machine learning deals with actually you finding a mathematical expression which allows you to estimate the quality of the model. So if you look at the function, the first function here, this one, and then you go back and look at the relative error, and since we now, or not the relative error, the absolute error, since we're now calculating derivatives, which one of these would you prefer? Let me give you a small hint. So you can use both, right? There's no and actually people, they mix these two sometimes. So the mean squared error puts a heavy emphasis on large outliers. So if you have something which deviates a lot, you square that one. So that puts actually a lot of emphasis on that. And if you have outliers and you want to emphasize them, then the mean squared error is interesting to use. You will see people combining the absolute value with the mean squared error, and then it has another name. It's called the Huber cost function. And there are many such different types of cost functions. But if you look at the, I just want, so which one of these should we prefer? So if you now think of the derivative of x, the absolute value with respect to x, we know that that one is equal to 1 if x is larger than 0, and it's minus 1 if x is less than 0. Now, it's undefined at x equal to 0. But it's in many practitioners put it equal to 0 because you just have a discontinuity. But in principle, it's undefined. But you will see in actual codes that people just put it to 0, which is mathematically not correct, but you put it to 0 because you want to have a value and to replace the discontinuity at 0. Now, if you look at the expressions which you then have, if you keep in mind that as a small hint, which would you prefer if you want to derive a simple equation? Yeah? And the mean squared. And as you will see now, with the mean squared, you're going to get a nice analytical expression. Whereas when you have the absolute values with the derivative of an absolute value, you get a discontinuity. And that means that you have to put in if statements. And we know that from a computational point of view, if statements, they always slow down the calculations. So if we can get a nice analytical expressions, we go for that. But both of these are viable ways by which you can gauge the quality of your model. Okay, so what we need to do next is actually to take the derivatives. And what I'm going to give you now is, and I'm going to leave that as a small exercise. You may have seen derivatives of matrices or vectors. These are some of these kind of hidden gems in linear algebra, which the mathematicians find boring and they never bring them up, but they're actually extremely important when you deal with machine learning. So have you seen derivatives of vectors and matrices with respect to vector? No, okay. So what I'm going to do is actually to bring up some material on that so that you can see the kind of expressions which you're ending up with. But one thing you could do, and I invite you to look at that as a small problem. If you look at the expression which we have here, this one, you could actually do it component by component. So the component by component means that you would simply now go back and take the derivative for a specific value of beta j. And then you can reframe that in terms of a matrix vector relation. So what I'm going to do now is I'm going to first set up the expression for it. And then I'm going to show you how you can derive these expressions. So let me just give you the answer when we take the derivative of the mean squared error. So what we're going to assume now is that the mean squared error is our cost function. So what we end up with then, and this is a notation, so beta hat is my optimal beta, the one which gives the best mean squared error. And with the best, this is as close as you get to the number of points which Norway receives when they try to qualify for the World Cup in soccer, which means 0. Okay, so we want the mean squared error to be 0. So beta here is now given by the minimization for all the beta values, which now we have is a vector of length p of c of beta. So when I put the hat, this is now my optimal value. Okay, so what I have next then is that I'm going to take the derivative of d beta, and I'm writing this as a vector. And this is now going to be the derivative of 1 of n of I equals 0 of n minus 1 of y of I minus. And I'm going to write this now in terms of a quantity which looks like an xi. I'm going to define it. You're going to see this in different disguises. So this kind of strange notation is actually the sum over j equals 0 up to p minus 1 of xij multiplied with beta j. Now remember now that this is a scalar. I also want to remind you that this matrix X is a matrix which has dimensionality n times p. So I'm going to use that way to label the design matrix. In other textbooks, you may see the features being the rows and the entries, the data entries or the inputs being the columns. So which notation you use or which way of ordering your data is up to you. But I'm going to use throughout this course, I'm going to use that as a notation. So I can rewrite this in terms of a d of d beta. And it's easy to see that since this has to be a scalar, I need to have the vector y minus x. So I can rewrite this. So this is a transpose. So when I now write everything in terms of a kind of compact matrix vector notation, this is a quantity I want to optimize. And that's why it's useful to revisit some of these derivatives of vectors and matrices with respect to either vectors or matrices. So if I take the derivative, so this becomes a scalar now. So keep in mind, this object here has a dimensionality of, so this is proportion, this is given by a vector. When I take this quantity here, this becomes a vector of dimensionality of length n. So we have y here transposed. And then when I multiply with that one, I just end up with a scalar. So this has a n, and then this quantity here is obviously a vector. So I'm just summing up of all the elements, and that becomes a scalar. And if I were to take the other way round, so the y minus xb times the transpose of the same quantity, I wouldn't get the right dimensionality. I wouldn't be able to calculate a scalar. So this is just a norm which we are or the inner product of a vector. Now I'm going to set up the derivative here, and then I'm going to show you how you can get these derivatives. So we have a delta C of beta, and this is going to be equal to -2 divided by n, and I'm going to get, sorry, not that one. This is going to be given by x transpose multiplied with y minus x times beta. And we want that to be 0. I can multiply away 2 divided by n, so we don't need to deal with that, and the minus sign. So that means that we have x transpose times y, which is equal to x transpose times x times beta. And that means that my optimal beta is given by the inverse of this matrix multiplied with a transpose and multiplied with y. Y is known and x is known. Everything on the right-hand side are known quantities. And this gives me the optimal parameter beta for that specific model I've chosen. So if I have a 10th order polynomial by this matrix inversion, so I invert the matrix which you see here. So everything hinges on that one. So if the matrix is singular or near singular, we run into problems. So when we make a polynomial approximation, what we actually have is that the columns of the matrix X should in principle be linearly independent because they represent different polynomial degrees. And then normally with a polynomial approximation for the model, there is often not a problem with inverting the matrix X transpose times X. So if we also look at the dimensionalities here, this matrix here is now given by P times P. The quantity you see here is a quantity which is also given by P times N, and Y has dimensionality or length N. So when I multiply X transpose with Y, I get a vector of length P, and I'm multiplying with a matrix of dimensionality P times P. So that gives me a vector of length P, which beta has as its length. So everything is correct here. Now, what you also see now is that your Y, if you plug it in, your Y tilde, which is given by this X multiplied with beta hat. This is the optimal model I have now. This is actually given, if we now plug in the results, this contains X multiplied with X transpose times X minus, and then we have X transpose times Y. So what you could think of now is that your optimal model is represented by a projection of Y into a space which is defined by the column vectors of the design matrix X. So you could think of your Y, the optimal model, in geometrical terms as a projection of the original dataset Y. So clearly, if X is the identity matrix, then this is trivial, right? Then Y tilde is equal to Y. That's also a useful test when you write a code. If you put X, your design matrix, to be the unit matrix, just ones along the diagonals, then you should just get back Y itself. So you can now think of, I'm actually gearing up towards the interpretation in terms of singular value decomposition when we are looking at linear regression here. Because there are nice ways by which we can relate standard linear regression with something which is called ridge regression and eventually also lasso regression. These are more alternative methods to what we are seeing here. Anyway, if you can invert this matrix, well, you solve the problem, right? But you see clearly that if the matrix here, which is a dimensionality P times P, if you have tons of features, which is not uncommon if you're dealing with the cancer research, and you want to link the specific tumor to the DNA sequences, then you can have millions of features. And you don't want to invert a million times a million matrix. Or if you're doing neural networks, you may actually have millions of parameters. And the matrix may just become too large for these methods. So these methods are typical methods which are useful when this P is normally smaller or equal, but in general, small, much smaller than N. So typically you can have, let's say, 10,000 patients and 30 features. Then the matrix to invert is just a 30 by 30 matrix. So from a computational point of view, that is a baby case. As soon as you run into larger dimensionalities, then we need to think of how to efficiently invert a matrix. But with the standard features, you will encounter many data sets. There is another famous data set, which is a credit card data from Taiwan, where you probably heard of that data set. So it has something like 30,000 entries. And the features are things like age of a person, education level, employment level, sex, etc., etc. There are some 20 features which label the credit card owner. And the data set deals with whether people would pay their credit card debt or not. So that's a true-false classification problem. Yes, no. And then you have something like 20 features. And then you try to find correlations in the data set between age, occupation, employed, unemployed, education, etc., etc., and see who's more prone to pay the credit card debt and who is less prone. So that's another type of data set where you typically have a matrix of dimensionality 20 times 20 to invert. But that's a